Welcome back to our Kalman Filter tutorial series. In this sixth and final video, we will be diving into a practical example of Kalman Filter in action. We will track a car moving at a constant velocity using noisy radar measurements. The radar provides us with both the position and the velocity of the car. We will build our Kalman filter step by step using the principles of Bayesian filter. So for that, I will download some libraries. I'll load some libraries here, and I will set up some simulation parameters. In our simulation, we will start with a time step of 0.01 seconds, and simulation duration is 10 seconds. This will give us a clear and detailed picture of the car's motion over time. Essentially, I'm building the time axis starting from 0 to 10 seconds. So let me just show it to you. So this is the time axis starting from 0 going up to 9.99 seconds. Okay. So now I will simulate the true motion of the car, that is car moving at a constant velocity. We will assume that the car starts at position 0 and moves at a constant velocity of 1 meter per second. And I use basic equations of motion here, that is the position of the car, the true position of the car is nothing but the initial position of the car plus the initial true velocity multiplied by the time axis. This is the basic equation of motion. And since our velocity is constant, I'm just going to be copying this 1 throughout the time axis. So that is the true velocity. Let me just run this code. So we have two plots here, one for the position, one for the velocity. The first one, the plot shows the true position of the car over time, assuming a constant velocity. The position increases linearly, as you can see. The x-axis is time axis and the y is position. And in the plot 2, this is velocity. So the second plot shows the true velocity, which is 1 meter per second. Now I'll introduce a process noise in the system. Essentially, in real life, the car's motion is not perfect. There are various factors like wind, friction, and road conditions and engine performance, etc., that introduce noise into the position and the velocity channel. So I'm modeling this process noise. Firstly, throughout this code, x will represent position and v will represent velocity. So this is the convention. And I'm introducing process noise by simulating a variance in the position channel and a variance in the velocity channel, initialized to 0.1. And then I'm using these variances, I'm generating a Gaussian distribution for the process noise in position channel, and again Gaussian distribution for process noise in the velocity channel. Once I've generated these two noises, I'm just going to add them to the true position. So the process noise in position channel is added to the true position to get the noisy positions, and the velocity process noise is added to the velocities, and that's how we get the noisy velocities. So let me just plot this. So here you can see the first plot is that of true versus noisy position. So the green line indicates the true position of the car, and the magenta line, which is oscillating around it, is depicting the noisy positions of the car because of the process noise. And similarly here, green line is indicating the constant velocity, the true constant velocity, but because of process noise, it is bouncing up and down around this green line. So far so good. We have been able to simulate true motion of the car, and we have also been able to simulate the noisy motion of the car due to process noise. The third part is we are observing this car through a radar which is capable of tracking its position and its velocity, but this radar is not accurate. It has got sensor errors. So we have to simulate these errors in the radar measurement. Once again, I have defined some variances both for position and velocity channels. So 0.2, and I'm going to generate noise both in the position channel. This is the radar measurement noise, and this is the radar measurement noise in the velocity channel. And once these noises are generated, I'm going to mix them with the true position and true velocity, as you can see here, and generate or simulate the noisy measurement, radar measurement in the position channel, as well as noisy radar measurement in the velocity channel. So let me just plot this. So this plot compares the true position, noisy position and the radar measurement. Actually, if you see the green line is the true motion, and I have, let me just enable the process noise also. Okay, let me rerun the code. So what you see here is obviously the green line has got hidden behind it. That is the true motion of the car, true position of the car. This magenta oscillations are the process noise, and the red dots are the corrupt radar measurements. As you can see, they are fluctuating very wildly over the true position of the car. So the first plot is for the position and the second plot is for the velocity. Here again, this is the constant velocity, and the red dots are the radar's measurement of velocity, which are very, very noisy and corrupt. So as far as Kalman filter is concerned, what the filter is going to see is this. So these red dots in the position channel and these red dots in the velocity channel are the inputs to the Kalman filter. And the idea here is that the Kalman filter should be able to seek these green lines, both in position channel as well as in the velocity channel, as closely as possible by eliminating these noise. So before we go there, let's start implementing the Kalman filter. Before starting the Kalman filter process, we will initialize some lists. Basically, these are the lists to store the output of the Kalman filter, which is the position output, the velocity output, and also the uncertainty associated with the position channel and the velocity channel represented by these lists. And I would also like to track the gains, Kalman gains in the position channel as well as in the velocity channel. So these are empty lists for that. Also, to kickstart the Kalman filter, we have to specify the current state of the system, the initial state. So all I'm saying is that I don't have any radar measurement available to me as of now. I'm starting a filter, so I have to give some information regarding the current position and the current velocity of the car. And here I'm assuming that the current position of the car is 0 and the current velocity of the car is also 0. Also, I have to specify some uncertainties associated with my current readings. So I'm saying that in my X channel, that is position channel, my uncertainty or variance is 1. This is just a pure guess. And in the velocity channel, it is again 1. So these are the initialization parameters. Let's have a look at the Kalman filter equations. So as we know, Kalman has two steps. One is the predict step, and the second is the update step, these three equations. So in the predict step, this is prior to radar measurement becoming available to us. So we have some initial estimate, which is represented by current, and we have to update this to come to arrive at the priors. So as I mentioned earlier, this X represent position and V represents velocity. Basically, we are required to calculate these priors, and we start with some estimate, initial guesses, and we use the equation of motion, which is shown here. So basically, this is the current velocity, the current guess of the velocity, multiplied by the time step and added to the current position of the car. So this will give me the estimate of the prior position of the car. And since I have a constant velocity model, so I'm just going to say that my current velocity is going to be my prior velocity. So this is these are two steps. Also, I have to calculate priors related to the variances of these two parameters, that is variance or the uncertainty associated with the position channel and the uncertainty associated with the velocity channel. So as far as position channel is concerned, there are three components to it. One is what the uncertainty associated with my current estimate, that is whatever guess I have made here. So that is this part. Now this uncertainty gets added to the velocity. Remember, velocity is also corrupt, and velocity is used to calculate the position. So I have to take this velocity into account. So I have some uncertainty regarding the current estimate of velocity, and that I'm going to multiply by the square of time step. So this is the second component. And then I have the third component, which is coming because of process noise. So we have process noise in the position channel, and that third component gets added like this. So this is the total uncertainty in the position channel. And then we have velocity channel. So I have some uncertainty associated with the current estimate of the velocity, which is here, initialized to 1. And then also we have a process noise in the velocity channel, which is represented by this. So I add both of them. So these two equations combined together, they make the predict step. So let's first see how it is implemented in Kalman filter. So for all the radar measurements, I'm going to loop through. So this, these four equations are the predict step, and they are actually, if you see, they are just simply representing, the first one is this, the second is this, the third is this one, which is implemented here, and the last is this one, which is here. So this is the complete predict step. So once we have calculated priors, at this point of time, our radar measurement becomes available, and now we have to take into account this radar measurement and calculate the posteriors. So this is the radar measurement that has become available to me, both in the velocity and position channel. And then what I'm going to do is, I'm going to use this radar measurement to calculate the prediction error in position channel. So radar is telling me that the car is at certain position, and my prior belief is that the car is at certain position. So whatever is the difference between them is the error in the prediction, which is represented by this residual x. Similarly, in the velocity channel, my radar is telling me that the car is traveling at certain velocity, and I also have a prior belief that the radar should be that the car should be traveling at a certain speed. The difference between them is the error in the velocity, prediction error in the velocity channel, and then I'm going to calculate Kalman gains. So Kalman gains, as mentioned earlier, also are nothing. So we have we have two Kalman gains, one for the position channel and one for the velocity channel. So here the first position Kalman gain is represented by this equation, where these two terms are just the same. They have come from the prior in the position channel, and this part, the measurement part, has come from the position channel in the radar. So that's how we are going to take into account the likelihood or the measurement part. And similar thing happens in the velocity channel. So we have our prior beliefs regarding the velocity of the car, and we then take the measurement noise in the radar's velocity channel and calculate Kalman gain for the velocity channel. Once these two gains have been calculated, then we just need to, these are the residuals. This is the residual or the prediction error in the x channel. We multiply that with the Kalman gain in the x channel and update our prior belief, which is shown here in the x channel. Now this becomes the posterior, and the posterior in turn then becomes the current estimate. And in the velocity channel, again, this is the this velocity measurement has come from the radar, and we have some prior belief regarding the velocity. So the difference between them is the prediction error that is multiplied by the Kalman gain, and the velocity prior belief is updated, and that's how we calculate the prior. And once we have calculated priors for both position and velocity, we also need to update the uncertainties associated with them. So that is the posterior part. So we have 1 minus Kalman gain into the prior of the position, which gives you the posterior in position channel, and 1 minus Kalman gain into the multiplied by the prior in velocity channel, that gives you the posterior in the velocity channel. So these two are the posteriors, and these two are the priors, and these are nothing but the gains. So exactly the same things have been implemented in the code, starting from the Kalman gain. So if you see, once we have calculated residuals, the first Kalman gain is this in the position channel, and the second is in the velocity channel. So two Kalman gains have been calculated. Then we move on to the posterior part. So Kalman gain multiplied by the residual error in x, and then added to the prior in the position channel, and same thing in the velocity channel. And then we have to calculate the posterior variances of position and velocity. So essentially they are nothing but prior sigma in the x channel multiplied by 1 minus Kalman gain. So this is posterior sigma for the position channel, and same thing for the velocity channel. And then I'm going to save all these parameters in my lists, which I had initialized. If you remember, I had initialized lists here. I'll save all these parameters here, and this entire code is doing that. And I will also save my Kalman gain for each iteration. And then I'm going to update my current with the posterior in the position channel. Also, my current in velocity channel will become whatever is the posterior, and similarly all the sigmas in the current both for x and y will be initialized by the posteriors. And this whole loop will get executed again until all the radar measurements have been taken into account. So let's run this code. Okay, I have to run this code first, and then run this part. And lastly, I am just converting all these lists into arrays for the plotting purposes. So this is just a little bit of housekeeping. And then I'm going to generate various plots. So this is the first plot. Let's see. Okay. So the first plot shows the Kalman filter estimates of the car's position, this blue line. This is the output of the Kalman filter. And as you can see that in spite of having very, very poor radar measurements, very, very noisy, the Kalman filter has been able to quite a degree, quite a bit of reasonable performance. The filter has been able to track this green line, which is the true position of the car. Similarly, when we see the velocity, this green line is the true velocity of the car. As you can see that in spite of having very corrupt radar measurements of the velocity, this blue line is the output of the Kalman filter, which is trying to track this constant velocity, and the blue fluctuations are much lesser than in comparison to the radar measurements. So Kalman filter is doing its job as intended. Next is we'll see the Kalman gains for both velocity and position channel. So as you can see, it starts off at a very high level, 0.85, and very quickly it converges to almost half. And similarly in the velocity channel, very quickly it converges to half. Then we are going to plot the PDF of the velocities. Remember, velocity is a constant. So there are 3 plots here. One is the process noise on the velocity is shown by this orange PDF. So we see that this orange PDF is slightly peakier in comparison to this red one. This red is radar measurement of velocity, and we know that radar measurements are more corrupt in comparison to the process noise. So you see a very flat Gaussian curve here. And then when we combine both these together, we get a Kalman filter output, which is depicted by this blue line. And as you can see, it's a very peaky shape, signifying that the noise in the system has been reduced, the uncertainty in the system has been reduced, and we are centered at 2 velocity, which is 1 meter per second. And this Kalman filter is increasing that probability quite a bit by eliminating the noise. Lastly, and this actually is the essence of Bayesian filtering, multiplication of 2 Gaussian resulting in a third Gaussian, which is having a much lesser variance or standard deviation in comparison to the both of them. So essentially this process noise is nothing but the prior, and then this comes from the likelihood radar measurement, and both of them have been combined together to get the posterior, which is the output of the Kalman filter. Lastly, we will see the position error estimates. Now this is nothing but whatever is the true position of the car and whatever Kalman filter has predicted. The difference between them is the error. So that's what we are plotting here. And we know we would ideally like this error to be 0, which is shown by this red line. The x-axis is time axis and the y-axis is position axis. And as you can see that in spite of very, very poor radar measurements of the position, the filter is trying to keep the errors as small as possible, trying to hug this 0 line here. And it's not allowing the errors to build up in the system, which means that the Kalman filter is performing pretty well. Ideally speaking, it should reduce these errors to as much as possible, but practically speaking, there are limitations. There are certain tunings that are required to be done to the Kalman filter. So this winds up our entire series on Kalman filter. In this tutorial, we have seen how to implement a Kalman filter from a Bayesian perspective to track the position and velocity of a car with noisy radar measurements. We have broken down the process step by step, visualized the true noisy and filter estimate, and analyze the Kalman gain and estimation errors. I hope you have got good insights into how this filter works. Thank you very much.